it's 2:30, so let's go ahead and get started today. Good afternoon, everyone. How's everyone doing today?
Not too bad. How's your weekend?
Good, good. Yeah, I got vaccinated this weekend, so my left arm is really sore, but glad to get that done. And then my second dose will be in 3 weeks. So yesterday I was kind of out of it because it's I mean everyone reacts to the vaccine differently, but I was pretty tired yesterday. I think daylight savings also contributed to it too, so I kind of slept for half the day yesterday, uh, but it's good to have the vaccine. It's good to have that kind of out of the way.
That's a common side effect because I got mine too. Like the first one was the same. Like
Mhm.
I just wanted to sleep all day pretty much.
Yeah,
I was
yeah,
just
yeah.
tired.
Yeah. But it wears off after a day, and then now I feel good. So that's good. Okay, and so today, today we're going to be continuing on with our lecture notes, and so we're going to be continuing on with our set of external convection. And so I think last time we ended up with an example, and so I'm going to kind of go over just a little bit from that example again, and then kind of start going through the other stuff. So we'll be trudging right along. Another announcement I want to make is that homework 4 is posted, and so homework 4 is going to cover the convection stuff that we've been going over. Um, and so there's 3 problem solving questions on it and 1 short answer question, so pretty standard, and that's going to be due next Friday. So next week is our last week of lecture before spring break, and so I wanted to have it due right before spring break starts, so that so you don't have to worry about the class during spring break, and I can spend that time grading. Okay. And so homework's gonna be due next Friday at 11:59 p.m. Okay. And so check it out. When you guys get the chance, and then I think by the end of lecture on Wednesday, you should be able to do everything on the homework. Okay. All right. Any questions I can answer before we get started today? Okay. All right. So let's go ahead and get going. All right. So last time, what we were talking about was, this whole idea of convection heat transfer, right? And the big issue with convection heat transfer is really just only one thing, and that's solving for H, right? Remember, H here is our convection coefficient, right? Because once we have the convection coefficient, then we kind of know how to take it from there. And so we can either do thermal circuits. I think is probably the easiest way, but then we can also use it with the heat equation, stuff like that, right? But for general situations, usually it's a little bit too difficult to solve for H. And so the way we usually go about it is we use our non-dimensional numbers. In particular, what we solve for is the Wusselt number. Right. And so the Wusselt number, we give that the symbol NU. And in most cases, we're going to have a bar over it. This is going to be equal to H times L divided by KF. Okay. Where KF, remember, is the thermal conductivity of the fluid. L is just whatever the length is in our problem. And H, of course, is what we're solving for. Okay. And then what we saw in the last example is that based on a lot of experiments that people have run over the years, we can use what's called these Wusselt number correlations in order to solve for it, right? So I think the one that we used in the last example was the following. And so we said that Wusselt number was also equal to 0.664 Reynolds number to the 1/2 times Prandtl number to the 1/3. Okay. Where everything on this side of the equation here, these we can easily compute these either by looking them up in the table or by plugging in parameters in the problem. Okay. And so the way we go about solving these convection problems, they're all they're all going to be kind of the same thing, although it's a little bit of a lengthy process. And so, you know, what first thing we're going to do is we're going to find the Wusselt number correlation that matches up with our problem. Okay. And so what you'll see is that we'll see, I think 6 or 7 different versions of this equation that I've boxed on the right, depending on what the conditions are. Okay. From there, we'll plug in everything from those, and then from there we can solve for H. Okay. So far we've only just done kind of one situation, which is just laminar flow over a flat plate, where the flat plate is held at a constant temperature. And so when the flow is laminar and when the flow is over a flat plate, you know, we can use the Wusselt number correlation that we have up there. But under different conditions, like say we have turbulent flow, or say our plate condition has changed a little bit, you know, we're going to have a different Wusselt number correlation in order to solve for that. Okay. And so a big part of these convection problems is, you know, looking at the situation that you have, looking at the geometry, looking at the flow, determining whether it's laminar or turbulent, and then picking the correct Wusselt number correlation that goes with that, and then using that to solve for H. Okay. All right, and so to start today, you know, we'll first talk about turbulence and see how that affects our Wusselt number correlations, and then we'll talk about, you know, some slightly different other conditions as well. All right, any questions on this? Okay. All right, and so let's go over turbulent flow over an isothermal plate. Okay. All right. And so we've talked about turbulence quite a bit, you know, leading up to this point, but we haven't really seen how that actually affects our calculations. And so the way that turbulence is going to affect our calculations is by changing our Wusselt number correlation, right? And so just as kind of a reminder, you know, we've seen before that turbulence tends to enhance convection heat transfer. Right. And the reason it enhances convection heat transfer is because of the chaotic nature of the flow. Right? And so generally what we expect is that because turbulence enhances these, then their Wusselt number correlations will be higher than their laminar case. Okay. And in fact, this is exactly the case. And so, you know, I'm going to give you the two Wusselt number correlations here. So one I'm going to give you for the local one. So remember, when I say local, what I mean is just kind of local to just one specific spot. Right? And so when you have turbulent flow over an isothermal plate, this is the Wusselt number correlation. Right? So we have 0.0296 times Reynolds number to the 4/5 times Prandtl number to the 1/3. Okay. All right, so let's compare this just very quickly to the local Wusselt number correlation in laminar flow. Okay. And so in laminar flow, we had the following. Okay, and so in laminar flow, we had 0.332 times Reynolds number to the 1/2 times Prandtl number to the 1/3. Okay? All right, and so, when you compare these two, at first it might look like the laminar flow one is higher because the coefficient out in front is bigger, right? And so from laminar flow, we have a 0.332 out in front, but for the turbulent one, we have 0.0296. And so that's 10 times lower. But the big difference here comes in the exponent for the Reynolds number. And so for laminar flow, we only had an exponent of 1/2 for the Reynolds number, but for turbulence, we have an exponent of 4/5, and that actually makes a huge difference into what your Newton number is. Because remember, for turbulence, turbulence occurs when the Reynolds number is greater than 5 times 10 to the 5th. Okay. And so in order to reach turbulence, our Reynolds number has to be really, really high, right? And when we take this Reynolds number and we raise it to a value like the 4/5, that ends up with a much, much larger number than if you just take the square root of it, which is what you do in the laminar case. Okay. And so at first, these two correlations might be a little bit confusing, just because for turbulent flow you expect a higher Newton number correlation, but the primary reason we get a higher one is because of that exponent. It has less to do with the coefficient out in front. Okay, and so that's the local Newton number correlation for laminar or for turbulent flow. Sorry. So, are there any questions on this before we go over the average Newton number correlation? Okay. All right, so that's the local one. And so I'll show you kind of an application of that in a bit. But usually, the one that we want to use for our calculations is the average Newton number. Okay. And so this is the correlation for that. Okay. And so since we're doing the average, we're taking we have this little over bar, and all that's really going to change is just the coefficient out in front. Okay. And so instead of having a coefficient of 0.0296, our coefficient out in front is going to be 0.037. So not too much of a change. It's just slightly higher than that. Okay. Okay. Right. But honestly, for most cases, we can't actually use this correlation in a lot of cases. And the reason for that is, remember, this is the average Wusselt number correlation. So this is average over an entire surface, right? And so in order to actually use this, we have to assume that the boundary layer is turbulent over the entire surface or most of the surface. Which can happen. It is possible to get turbulence over the entire surface if we do something like we trip the flow, which is something that we talked about before. But more typically, you have a situation that looks like this. Right? Okay. And so you have a boundary layer that goes over the surface like this, and so we have flow coming in from the left. Right? And so the flow is going to strike the plate, and at first the boundary layer is going to start out laminar. And then it's going to go turbulent. Okay. And so since we have since we usually have a region where, part of our boundary layer is laminar, we can't just assume that the entire thing is turbulent. And so what we can do instead is that this creates what's called a mixed boundary layer. Where part of the boundary layer is laminar, and so we're going to use our laminar correlations for that. And then the other part of the boundary layer is turbulent, and then we'll use our turbulent, Wusselt number correlations for that. And I'll show you how to account for this on the next page. Okay. All right. Any questions on this?
Sorry, so the mixed boundary layer, is that like when you have both laminar flow that transitions to turbulent, or is it
Yes.
like the exact point? Okay.
Yeah. So when I say mixed boundary layer is that, over the entire surface, there's some of it that's laminar and some of it that's turbulent.
Okay, so yeah, that contains like the whole thing we're looking at here.
Exactly. Mm-hmm. Yeah. So basically what we're going to do is we're going to solve for the Wusselt number correlation, assuming that's laminar up to a certain point. And then after that point, we're going to assume it's turbulent. And so we'll have kind of an integral expression for that. Okay. All right. Any other questions on this? Okay. All right. And so let's go over, what you have to do for a mixed boundary layer. All right. And so for a mixed boundary layer, you're going to use the following expression. And this expression is going to be for the average Wusselt number for over the entire surface. Okay. Right, and so we're going to have Wusselt number, and I do sub L here because that's going to be over the entire length. And we're going to do 1 divided by L times integral from 0 to xc of the laminar Wusselt number correlation with respect to dx. And then another integral from xc to L of the turbulent Wusselt number correlation. Okay. And so there's kind of a lot of terms here, and so let's define what each of these are. Right. And so first, let's talk about the Wusselt number correlations that we plug in here. And so NU lam here, this is going to be the local Wusselt number correlation for laminar flow, right? With emphasis on local. Okay. And so the one you're going to plug in is 0.332, a Reynolds number to the 1/2 with respect to x times Prandtl number to the 1/3. Okay. And remember, the thing that you're integrating here is x. And so what you're going to plug in is you're going to plug in for the Reynolds number with respect to x. Okay. And so you're going to plug in 0.332 times u infinity times x divided by the kinematic viscosity raised to the 1/2. Prandtl number to the 1/3. Okay. And so that's what you're going to plug in for new NU lam. Okay. Right. And then NU turb, this is going to be the turbulent, local turbulent Wusselt correlation. Okay. And this one, you're going to plug in, the expression that we had just on the previous page. Right? So it's going to be 0.296 times Reynolds number to the 4/5 times Prandtl number to the 1/3. Where again, you're going to plug in for the Reynolds number here. Right? And so Reynolds number here, we're going to plug in for U infinity x divided by nu raised to the 4/5 power. Right? And so those, remember, when you're using this formula here, you have to plug in the local Wusselt number correlations, right? Otherwise it's not going to work. And then XC, I'll write out the formula for XC on the next page, but XC is basically going to be the location where we transition to turbulence. I'll just write it on the next page. All right, any questions on this before I give you the formula for XC? Okay. All right, so XC, location, where transition to turbulence occurs. Okay. And remember, transition happens when your Reynolds number reaches 5 times 10 to the 5th, right? And so we can basically take Reynolds number is equal to 5 times 10 to the 5th, which is equal to the velocity multiplied by the viscosity times XC, right? And so basically we can just work with this expression and solve for XC. And what we get is XC is equal to nu over U infinity times 5 times 10 to the 5th. Okay. Okay. And so when you're solving problems and you see that you have laminar flow over the entire surface, or you reach laminar flow at some point, and so what you need to solve for is the location where the transition occurs, and that's going to be your XC. And so this is you can almost think of it as like the critical location. Okay. All right. And so that's what you do when you have a mixed boundary layer. And so you basically take just a combination of the laminar one and the turbulent one, and you integrate that, separated by this, critical location XC, right? But everything that we covered so far is for when you have when your surface is at a constant temperature. What can also happen sometimes in practice is that you can assume that your surface is releasing a constant amount of heat flux. Okay. And so basically these are for situations where, you can kind of assume that your surface is going to, be changing temperature all throughout, right? So let's say that, we have a surface like this, and basically up until this point, we've assumed that this entire thing is the same temperature. But what can happen more commonly in practice, especially if you have a very long surface, like say you have a fin or something, is that, you might have one temperature here. Okay. We'll call this T1. And then, as you go along the surface, the temperature is either going to cool or it's going to heat up depending on, where, what's going on. And you might have a different temperature here, T2. Okay. And so if your surface here is not all the same temperature, or is, it's not reasonable to assume so, that's going to change your conditions a little bit. Okay. And so I would say, the Wusselt number correlations that I'm going to give you now, this is probably a bit more common from what you would expect from a fin, because oftentimes for a fin, you have a pretty long surface, and you're not going to have the same temperature all throughout. But what you can assume is that the heat flux might be constant all throughout. Okay. And so in those cases, this is basically going to change your Wusselt number correlations. Okay. And so, when you're doing these problems, you need to kind of read the problem carefully and see, what your surface condition is like. And so if your surface is at a constant temperature, you can use all the Wusselt number correlations that we've gone over previously. But then if the problem says that, your surface is at a constant heat flux, you're going to use these ones instead. And so first one we'll go over is the local one. Okay. Local and laminar. Okay. And so if you have laminar flow, the local Wusselt number correlation is given by the following. And so we have NUX is equal to 0.453 times Reynolds number to the 1/2 times Prandtl number to the 1/3. Okay. Right. And so you can see this looks very similar to our isothermal case. The coefficients here are the same. And so your Reynolds number and Prandtl number, they're raised to the 1/2 and the 1/3 power, respectively. And so the only thing that changes is just the decimal out front. And so instead of having 0.332, when you have a constant heat flux, this raises the Wusselt number correlation just kind of slightly. And so now we're at 0.453 instead of 332. Okay. But you can use this in exactly kind of the same way. It's just that if your surface condition is different, then that's going to change your Wusselt number correlation.
Professor, I had a quick question.
Sure. What's up?
So does the lower coefficient indicate anything about the convection heat transfer or the conductive?
You mean this decimal out in front?
Yeah, and just how it relates to like the H bar times L over KF.
Yeah. So for cases with constant heat flux, you're going to have a slightly higher H than if you have let's say you have the exact same flow conditions, so exact same velocities and exact same Reynolds number, stuff like that. If you can basically assume that your surface is at a constant heat flux, you're going to end up with a higher H bar, just because of this number out in front right here. Yeah. Right. Does that answer your question?
Yeah, it does.
Great.
What about KF? Would that just be the same?
Yeah, so KF here is the same. So assuming that your fluid properties are kind of the same in both cases. And so, assuming everything else is the same, but if you only just change from a constant temperature to a constant heat flux, then you're going to end up with more convection heat transfer here with this guy.
Oh, okay, that makes sense.
All right, and so that's for laminar flow. And so now let's go over turbulent flow. Right, and so this is constant heat flux, but now we have turbulent flow. Okay, and again, this is the local Wusselt. Right. Right. And so we have Wusselt number is equal to 0.0308 times Reynolds number to the 4/5 times Prandtl number to the 1/3. And so again, very similar. And in fact, with turbulent flow, you see much less of a difference. And so if you remember for our turbulent flow for the isothermal plate, our decimal out in front was like 0.029 something. And so this is very slightly higher than that. So they're basically indistinguishable. Okay. All right. And then if you take the average of that, and so let's say that we took this, this expression right here, and we just average it over the plate. So we took the integral and we divided by L. The difference is even smaller. Right? And so let's say that we have laminar flow, but now this is the average Wusselt number correlation. And so what we get from this is the following. And so what we have is Wusselt number with a bar is equal to 0.68, Reynolds number, the 1/2, Prandtl number to the 1/3. And so if you compare this to the isothermal case, the only difference is in this coefficient out in front, right? And so we go from 0.664 to 0.68. So it's basically not really a difference, okay? But sometimes, that small difference can make, a big impact depending on the situation. So I at least wanted to cover this. I would say for this class, I don't think I've written any problems, at least not in the homework that use these correlations here, but I did want to make you guys aware of it, in case you run across, a situation like this in practice. Okay. All right, any questions on this?
Sorry, the Prandtl number should be to what power?
1/3.
Okay.
Yeah.
So I looked
Prandtl
like
number
a
is-
5 now.
Yeah. Prandtl number is almost always going to be to the 1/3, at least for external convection. All right. And so now that we've seen basically all the Wusselt number correlations that are available to us, so it's a lot, and I've actually written a summary document for you as well, that kind of summarizes all these things in kind of a nicely formatted document. But that covers everything in convection. So I think I'll wait until I give it to you. Right? But now that we have all these convection, all of these Wusselt number correlations, now the challenge is, how do we select the right one for a situation? Okay? And so I'm going to introduce you basically what I call the convection problem solving recipe. And so, you can basically apply this recipe to, almost any convection problem that we're going to go over in this unit. And even though it's fairly long and usually it kind of takes a while, usually, if you follow these steps, you're going to be in pretty good shape. Okay. All right. And so, what you'll see from the homework, at least for the first problem, I basically kind of walk you through these steps. So I know the first problem that you look at in the homework, it's going to be intimidating because there's like 6 or 7 different steps. But what you'll see is that a lot of these steps are going to be just kind of very quick, just one-liner. Some of them are just kind of yes or no kind of questions. Okay. All right. And so the first step for doing any kind of convection problem is to identify the flow geometry. And so what this means is basically, you should classify, what kind of flow that we have, right? Just in terms of just the shape of the flow. So far we've only gone over one shape, but later on in the lecture today we'll go over the second shape, which is cross flow over cylinder. Okay. And so when you're identifying the flow geometry, all I need is basically just a word or something. So, one option for this would be like flat plate, which is what we have been doing. There's also cross flow over a cylinder, which is what we'll go over later today. Okay. And there's even Wusselt number correlations for kind of everything in between. So there's things for spheres, there's things for boxes, there's lots of different correlations. And so the first step to basically choosing the right Wusselt number correlation for your situation is just to identify, what the flow geometry is going to look like. And so this is usually just one line, and you usually can see it just from whatever the image is. Okay. And so that's step 1. Step 2 is to specify the film temperature and write down all the fluid properties. And so remember, the reason we have this film temperature is because a lot of the fluid properties that we're looking at, things like viscosity, things like the Prandtl number, things like the thermal conductivity, these depend pretty heavily on temperature. And so we want, when we're reading these things off a table or we're getting these from online, we need to make sure that we get the temperature correct. Okay. And so the way that we do that is we take, the reference temperature, which is the average between the free stream temperature and our surface temperature. Okay? Some problems will just give you the film temperature. And so if you look at the homework, I basically tell you that, assume the film temperature is like 20 degrees C, or assume the film temperature is 30 degrees C. And so in those cases, you can just use what I tell you. But in other cases, you might have to take an average for that. Okay. And then once you have the film temperature, you're going to use this to evaluate the properties. And so the properties that you need to look up are usually three. And so the ones that you look up are the kinematic viscosity, which is new. Okay. The next thing that you look up is the thermal conductivity of the fluid, which is Kf. And the last thing that you look up is usually the Prandtl number. So that's the last one. Okay. All right. Step 3. And so step 3, now that you know the the properties of the fluid, you can go ahead and start computing the some things, right? So the first thing you should compute is the Reynolds number. Okay. And if you remember, Reynolds number is U infinity, which is the velocity of the free stream, multiplied by some length divided by nu, which is the viscosity. Okay. And then from this Reynolds number, you need to answer a very important question. Okay. So you need to answer whether your flow is going to be laminar or whether your flow is going to be turbulent. And remember, this is really important because, depending on whether the flow is laminar or turbulent, that's going to change which Wusselt number correlation that we're ultimately going to use. Okay. Step number 4. And so step number 4 is to decide whether we need a local convection coefficient, an average convection coefficient, or if we have a mixed situation. And so I would say, 99% of the time you're going to need either average or mixed. Okay, because a lot of times we're interested in the overall heat transfer from a surface. We usually don't care too much about the little details. And so, most of the time we're not going to need local. And so you're either going to, use an expression for the average convection coefficient over the entire surface, or you have a mixed situation where you have, some parts that are laminar and some parts that are turbulent, and you need to account for both of those at the same time. Okay. But make sure that you kind of write it down kind of explicitly so that you know which equations you're going to use. Okay. And so once you're done with that, then we're at step 5. And step 5 is to, now that we've taken all of these things into account, we know the flow geometry, we know the Reynolds number, we know, whether we want an average or a mixed case. Now you just have to select the appropriate Wusselt correlation. Okay. And you have a lot to choose from, depending on the situation. So you want to make sure you kind of do steps 1 through 4 so that you can make the best decision for which correlation that you want to use. Okay. All right. Any questions on this before we jump into an example? Okay. All right. So let's go ahead and do an example. All Right. And so let's say that we're designing our own brick. So let's say that we're building our own computer, and right now we're dealing with the fan. Okay? All right. And so the situation looks something like this. And so let's say that we have a fan that we want to select. Right? And this fan is going to be rotating. And it's going to be blowing air. And what we're interested in is, what velocity or how powerful does our fan need to be in order to cool our machine. Okay. And so what we don't know in this case is actually going to be U infinity. Okay. But we do know everything else about the system. Right? And so let's say that we have the temperature of the air is going to be 20 degrees C, and so it's essentially room temperature, a little bit colder than that. Okay. We know that we're going to be blowing this air over a flat computer surface. Okay. And so let's say that this is a fin that you have in your computer. And so the fin is at a constant temperature. And we'll say that this temperature here is 45 degrees C. Okay. We'll say the length of this fin is 10 centimeters. Right? And then the width of the fin going into the page, we'll say this is going to be 5 centimeters. Okay? So we know the total surface area. And we also know that that your computer is going to be outputting 5 watts of power that goes through this fin. Okay? And so what we need to do is we need to basically solve for solve for the airspeed that we need to basically keep this computer cool. Okay. Right, because basically what we're saying is that if the surface temperature exceeds 45 degrees C, then it's either going to damage the chip or it's going to melt your system, which is obviously not good. Okay. All right, and so it's a little bit of a twist on on the problems that we've looked at before, but what you'll see is that we can use the same convection problem solving recipe that we went over here, and use this to solve for this problem. Okay. All right, any questions on the problem setup here? Okay. All right, and so let's follow the convection problem solving recipe, and then let's start filling in each of those parts. Okay. All right, and so step 1 of our recipe here is to just identify the geometry. Right now, this is kind of it's kind of a dummy answer because we only know one geometry so far, but we should still write it down. And so our geometry in this case is just going to be flow over a flat plate, right? And so you can kind of see that in the image. And so in the image you see we have a fan that's blowing air over our computer chip, which is we're just assuming that it's just a flat plate. Okay. Okay. And so that's simple enough. And so now that we've identified the geometry, now we need to start looking up the fluid properties. All right, so step 2 is determine the film temperature and look up the properties. Okay. And so in this problem, we're not given a film temperature, and so we can compute it based on the other temperatures in the problem. Right. And so when we're not given a film temperature, we just simply take the average of the fluid temperature and the surface temperature. And so there's going to be T infinity plus TS divided by 2, right? And so it's just going to be kind of just, what is in between those. And in this problem, we know that T infinity here is 20 degrees C, and we know that our surface temperature is 45. And so you take the average of that. So you have 20 plus 45, which is 65, divided by 2 is 32.5 degrees C. Okay. And now that we have, the film temperature, we can look up the properties either in a table or, honestly, for the homeworks, what I did was I just searched up, properties of air at so-and-so temperature. Right? Okay. And so if you want to use the book table is table A.4. Okay. And so the A means that it's in the appendix, so it's kind of near the back of the book. And then what you'll see in that table is that, there's different properties for air at different temperatures. And so for this one, since we have a film temperature of 32, we convert that to Kelvin, that it's a little bit over 300. So it ends up being like 305, but it's close enough to 300K that we can just kind of, round down to it. Okay. And these are the properties that we get. And so we get a kinematic viscosity of 15.89 times 10 to the 6. 10 to the minus 6 meters squared per second. Then we get a thermal conductivity of 26.3 times 10 to the minus 3 watts per meter K. Okay, and the Prandtl number we see is 0.707. And so luckily for us, Prandtl number is something that we can just compute, or we can just look it up in the table, okay? Because it's used so often for thermal analysis that, instead of listing both the thermal diffusivity and, and the viscosity, they just kind of take the ratio for you. So it's kind of a nice thing. Okay. And so now that we have all the fluid properties, now we move on to computing the Reynolds number.
Professor?
Yep.
How did you get 300K or Kelvin?
I just basically took the temperature in degrees C and I added 273. So it's just the conversion between Celsius and Kelvin. So it's not quite 300, but you get something that's a little bit over 300, but it's close enough that we can, because otherwise we'd have to interpolate and it's kind of a pain in the butt. And so usually if you're close enough, then that's usually just fine. Yeah.
Okay. So do you round down?
Yeah. So you can either round up or down, whichever one you're closer to.
Okay.
But since we're going to be virtual all this semester, typically what I do is I just Google search it. And I just search, properties of air at, 32.5 degrees C. And usually there's like the first Google link will tell you what it is. That's usually faster than looking up in a table.
How far can we round it up and or down?
Usually if you're within 10 Kelvin, I'd say that's usually fine. And so even if our film temperature here was like 310 Kelvin, I'd say that's still okay to round down. Anything beyond that, you might want to interpolate. Yeah.
Okay, thank you.
Mm-hmm. Okay. And so the next thing we have to compute here is the Reynolds number, but we can't do that yet because we don't have the velocity. Right? Because remember, Reynolds number is U infinity times L divided by mu. But since we don't have the velocity yet, and that's what we're solving for, we can't actually compute this yet. Okay. Which kind of brings us to an interesting point, because remember the Reynolds number, determines whether we're laminar or turbulent, and that makes a big impact on what methods we're going to use to solve. Right? And so at this point, we kind of have to make a decision. We have to make an assumption. And so just for kind of ease of computing, and also because I know the answer already, let's go ahead and assume that the flow is laminar. And so, for your situations, where obviously, you're not going to know the answer to every problem before you do it. I'd say, making the assumption that it's laminar first, I think it's not a bad assumption, especially because it'll lead you to a solution much faster than like a mixed boundary layer or a turbulent one. And so I think it's, usually it's okay to assume laminar first. We're going to check it later just to make sure that, we're still good. And then, you can go from there. And so if you assume laminar, and then later on you compute it and you end up with turbulent flow, then what you can do is you can go back here and kind of revise your methods. But starting with an assumption of laminar flow, I think is usually reasonable for flows, especially for this one where our length is so small. Our length here is only 10 centimeters, and so usually in those situations, the flow probably won't have enough time to develop into turbulence, and so making this assumption is usually okay. Okay. All right. Any questions on this so far? Okay. All right. So that's the Reynolds number. And so step four, we need to decide, whether we need a local Wusselt correlation, an average one, or a mixed one. And so in this situation, since we're, we want to look at the overall heat transfer for the entire, surface, we don't want local, okay? Because remember, local is just, the convection coefficient at just a single spot, and that can change, as a function of x. But what we want is kind of the overall convection coefficient for the entire surface. And so, we either want average or mixed here. We can also cross out mixed because of our assumption of laminar flow, okay? And so in this case, we just want, the average Wusselt number correlation. Okay? Okay. And so now that we have all that information, we can go ahead and select our Wusselt number correlation. And in this case, where we have laminar flow and we want the average one, that gives us, and our plate is at a constant temperature, it gives us the following expression. Okay. And so, we're going to use this expression. So 0.664 times Reynolds number to the 1/2 times Prandtl number to the 1/3. And this is equal to the average convection coefficient over the entire surface, or H bar, multiplied by the length of our surface divided by Kf, which is our thermal conductivity. Okay. All right. And so usually at this point in the problem, what you can do is you can plug in for Re, you can plug in for Prandtl number, and you can solve for H. Okay. This problem is a little bit inverted because what's unknown here is actually going to be the Reynolds number. Okay. And so we're actually going to be solving our expression for that. But we actually have everything else that we need in this problem. Right? So we know what 0.664 is. We know the Prandtl number because we looked it up. We know the length of our plate, and we know Kf, because we looked it up in the table. And we can actually solve for H, depending, based on what we already know from the problem.
Professor?
Yep. Mm-hmm.
I'm a little confused. Is this not flat plate with constant heat flux?
This is flat plate with constant temperature.
Ah, okay.
Yeah. Mm-hmm. Although technically it is constant heat flux as well, because we do have this heat flux of 5 watts coming in, and we are going to use that in a second. And so you can definitely make the argument that you can use this this correlation as well. because certainly this, certainly we have a constant heat flux here. But in this case, when you have, since we know the surface temperature all throughout, and we're assuming it's 45 all through, then in that case, we're going to use our constant temperature surface condition instead.
Okay.
Because from the problem, what we know is that we have a constant amount of heat that we need to offload, right? And so we have QF. So remember, QF was given to us as 5 watts, right? And so we know that. And we also know the temperature difference in between the surface and the fluid, because we're given both the surface temperature and the fluid temperature, right? And so we can actually compute that. And then if we fill in the rest from our Newton's law of cooling, then what we have is h bar times A times Ts minus T infinity, okay? And so we have everything else in this expression. And so all we have to do is just solve for h bar. And so h bar is going to be QF divided by A times Ts minus T infinity. And then now what we can do is we can take this and plug it in up here, and then use this to solve for the Reynolds number. Okay. And then from the Reynolds number, we'll be able to solve for the, solve for the velocity. Okay. All right. Any questions so far? Okay. All right. And so when we plug in this expression for h up here, and then if we solve for our e, we can basically just divide both sides of the equation by 0.664 and Prandtl number to the 1/2. Okay. And then what we get is, we get Reynolds number to the 1/2 is equal to QF times L divided by 0.664 times Prandtl number to the 1/3 times KF times area times Ts minus T infinity. Okay. Where area here, we're just going to plug in the product of the length and the width, right? Both of which are given to us in the problem. And so if you plug in for everything on this side of the equation, you take the square root of both sides, okay? What you get is a Reynolds number of 6.61 times 10 to the 4th. Okay. And so that's basically what our Reynolds number needs to be in order to achieve this thermal condition.
Wouldn't we square both, like to the top power 2?
Yeah. Yes, you're right. We should square both sides. My brain is thinking like 3 steps ahead right now. I said 3 out loud and I put 3 on the page. There we go. Okay. And luckily for us, we see that our Reynolds number is less than 5 times 10 to the 5th. Okay. And so this confirms our assumption here that, our assumption of laminar flow here is confirmed, right? Because if this was greater than 5 times 10 to the 5th, then, we would see that we would require a higher Reynolds number, and we need to go back and change our Wusselt number correlation. But in this case, that's not the case, because we end up with a laminar 1 anyway, okay? All right, and so what you can do now is you can take the Reynolds number, which you know is U infinity times L divided by nu, okay? And what you can do from here is you can solve for U infinity, what you get is U infinity is equal to 10.5 meters per second. And so in order to cool your computer, basically your fan needs to blow air at 10.5 meters per second. Okay. And so at that point, you can look at, you probably go to some, wherever you're buying your electronic parts and see, which fan is able to produce this amount of airflow. All right. Any questions on this example?
I have a quick question.
Sure.
So if your assumption was wrong and you got something greater than 5 times 10 to the 5th, the Reynolds number, how would you know whether it were mixed or turbulent?
Yeah. And so in that case, you would start with an assumption of mixed, because usually when the flow is either all turbulent, usually that happens when you purposely trip turbulence. And so if you have something like, say you have like a barbed wire here or some kind of trip wire, that's basically going to make it so that you kind of force turbulence from the very beginning. In that case, you can just use a turbulent boundary layer. But in this case, we didn't say anything like that. And so even if we end up with a turbulent boundary layer, there's probably still going to be a significant portion where, it's laminar. Yeah.
Okay.
Mm-hmm.
Thank you.
Yeah. And so kind of an exception to this is that, and you'll see this in practice too, that the flow might be so fast that you might achieve turbulence like within the first 1% of your surface. And so if you compute x sub c, and x sub c in this case, let's say that it's 0.1 centimeters, just for kind of demonstration's sake, and the total length of your surface is 10 centimeters, then you can basically assume that the entire thing is turbulent, because less than about 1% of only 1% of your surface here is laminar. So you can reasonably assume that the entire thing is turbulent from there. But it's kind of a case-by-case kind of basis. So if in kind of the most general case, you can assume that it's mixed, and then that will always work. If anything, it'll just be a little bit time-consuming. Okay. Any other questions on this example here? Okay. All right, and so far, we've done a lot of examples with the flow over flat plate, but that's not the only external convection situation that we can have. And so the other situation that we can have is what's called a cylinder in cross flow. And so schematically, it looks something like this. And so you have a cylinder, and we're viewing at it from down the barrel, and you have fluid velocity here, okay? And then what's going to happen is that the flow is going to go basically around the cylinder. Okay. And usually you're going to know the diameter of the cylinder. That's going to be important for the Reynolds number later, okay? And this presents kind of a different kind of flow situation than our flat plate, right? And so what you'll see is that, we'll have a different Wusselt number correlations for this. Okay. Right. And the reason, we're going to have different Wusselt number correlations is kind of one big thing, right? Because for the flat plate, what we had always assumed, and it's a very reasonable assumption for a flat plate, is that, we always assumed that the boundary layer was always attached to the flat plate. Okay? But that's not the case for the cylinder, because for the cylinder, we have a lot of curvature now that we need to deal with. Okay, And so what the curvature is going to do is the curvature is going to cause our boundary layer to separate from the surface. And so boundary layer separation is, something that you may or may not have covered in fluid mechanics because it kind of appears at the very end. But kind of the upshot of this is that whenever you have a boundary layer separate, then it's going to form a wake in your flow. Okay. And the wake has kind of specific thermal properties as well as fluid properties that that will affect our convection heat transfer. Our question. So would the boundary layer be like a V shape and then have the inside of the V be turbulent? We'll go over the shape of the boundary layer on the next page. Yeah. Mm-hmm. All right. Any questions on this? Okay. And so let's talk about the wakes and how the boundary layer kind of develops in these flows. Okay. Okay, and so let's go over a laminar case first. So let's basically assume that the entire fluid or the entire boundary layer is laminar up to the point of separation. All right, so let me go ahead and draw my cylinder here. Okay, and then we have fluid that's coming at it from the left. And so, if you have a laminar flow, the surface is going to look like this. And so right at the point of contact, or so when the fluid strikes a cylinder, you're going to have a boundary layer that starts to form. It's going to form on both sides. Okay. Right. And since we're in laminar flow, this boundary layer here is laminar. Okay. But then at a certain point, and actually there's been a lot of experiments that have been done about this. Okay. And we'll say that the point where it separates, we'll say that this is going to be 80 degrees here. Okay. At 80 degrees, what's going to happen is that the boundary layer will separate and form a wake. Okay. And so at this point right here, this is our point of separation. Okay. Because up until the point of separation, the boundary layer is going to be hugging up next to the surface, going to be hugging up next to it. And then once it separates, then it kind of forms this kind of wake behind it. Okay. And so this region right here is known as the wake. And so in the wake, what you have is kind of, twisty, chaotic flow. Okay. And if you remember, when we talked about turbulence, right? The main reason turbulence enhances heat transfer is because of all the twisty, chaotic, rotating flow that's in turbulence. And so you have kind of the same thing in the wake. And so in this wake region, because you have this kind of, flow that doesn't follow a straight line, what you have is basically enhanced heat transfer in the wake region. Okay. Okay. And so just to summarize, so in laminar flow, the flow separates pretty quickly. And so it has a separation angle about 80 degrees, give or take a few. And then you're going to have a very large wake. And so in the wake, you're going to have enhanced heat transfer. Okay. All right. Any questions on laminar flow here? Okay. So that's laminar flow. And so now let's go over the turbulent case. So let's say that, we have either the same cylinder and we increase the velocity, or, we just have a bigger cylinder like this. Okay. All right, so let me draw my cylinder again, just like that. And so we're going to have flow that's coming at it from the left side. And so just like before, at the point of contact, we're going to have, a boundary layer that's going to start to form. Okay. But unlike the laminar case, surprisingly, what happens in turbulence is that the boundary layer stays attached for longer. And so what you have is, the boundary layer is going to start out laminar just like it does. And then eventually the boundary layer is going to go turbulent. Okay. It goes turbulent, but it stays attached. Okay. But it doesn't stay attached forever. And at a certain point, the turbulent boundary layer is going to separate and form a smaller wake. Okay. And so just like before, we have a point of separation. Okay. And then that point of separation happens at a larger angle. Okay. And so of course, this angle kind of differs case to case, but approximately it's going to be at 140 degrees. Okay. And so what we have here is that the presence of turbulence will delay boundary layer separation. Right. And so, if we delay boundary layer separation, this means that we're going to end up with a smaller wake. Okay. Smaller wake, but typically more enhanced heat transfer. Okay. All right. Any questions on this turbulent diagram here? Our question. So is that why submarines have a conical shaped cylinder to them? Yes, actually, yeah. So actually, that gets a lot more into fluid mechanics, but the shape of like a submarine and even airplanes and sports cars too, they all have kind of a what I call like a contoured shape. And so you don't see, so you don't see submarines that are shaped like a box. And so the reason, you have that is so it kind of helps to guide the boundary layers all throughout. Because for these kinds of device or these kinds of vehicles that are driving through flow, whether it be water or air, you want to minimize this wake region as much as possible. Because the less wake that you have, the less drag that you're going to have as well. And the less drag means that your engine is going to be more efficient, and you generally go faster, which is usually what you want to do in these kinds of vehicles. Yep. All right, any final questions before we wrap up for today? All right, so that's all we got time for. So thank you guys for tuning in today. And so remember, homework 4 is posted, and you should be able to get through, I think, the first 2 problems on it. And then Wednesday, once we finish up some cylinders here, you'll be able to do the last bit. Okay? So thank you guys for tuning in. Hope you guys have a good rest of your day, and I'll see you guys on Wednesday.
Thank you, Professor.
Thanks, guys.
Thank you, Professor.